good day to you. It is the 5th day of August in 2025. This is Anna Galactic bringing you the secrets of the universe. Astronomy is mostly about light. It does behoove a scientist to understand what is light. How does it propagate through space? How does that photon find its way to a telescope or a human eye on Earth on a bullet straight trajectory, a strict linear trajectory, when it's actually a spherical surface? We know that it's not precisely a particle when it's traveling through free space. That little tiny photon, when it detaches, how does that little tiny photon, a quantum of energy, which then traverses space, it expands essentially as a spherical wavefront? If you do picture that, you'll realize that it has to contact your telescope or your eye, because an expanding sphere will hit everything in the universe until it's absorbed. When it is absorbed, it acquires the scientific explanation, which is no explanation at all according to Einstein and others, including myself. The wave function, which is a spherical wave function, collapses, which apparently defies relativity. It somehow transcends the speed of light, because a spherical surface, as it is expanding from that atom in that star, acquires a huge radius, and therefore it has an enormous circumference. But it contains information, all of which is reacquired at the destination. This leads to several paradoxical questions which essentially comprise the quantum paradox system. It applies to light. It also applies to the electron. Today we're going to be completing our proof sequence for the quantum of gravity, which is a somewhat open-ended question, even if one were to somehow home in on the answer to what is the smallest measurable unit of gravity, which would be the quantum of gravity by definition. Then it would raise a second problem, which essentially would have to be solved simultaneously, which is, since you've discovered the quantum of gravity, you would have to then explain how it is that gravity appears to be continuous through space, and yet you've found the quantum. The way we express that paradox is that gravity is monopolar, which means it's not dipolar. Electromagnetism is dipolar because it has a north and a south, as we phrase it. So it has two poles, the plus and the minus, which is well known in electrodynamics. Gravity appears to be a form of magnetism because it exhibits centripetal space force, as we discussed in the prior video. However, if so, it violates Newton's law of conservation, which is fully accepted in physics. Of course, I do too. That is called the conservation of force. But in this case, you're talking about what has sometimes been dubbed a pseudo-force for this reason. Gravity does not exhibit motion. Therefore, under one model, which is fully acceptable, I'll just say with a footnote, everything has a footnote at this scale and level. If it is the quantum of gravity that is bending space, that is the model that space-time is curved, if so, then it is essentially, you could either say exhibiting a force, but that is denied by about half of physicists. It's a strange situation. It is part of the quantum paradox because we're dealing with a quantum quantity. Somewhat redundant, but not really, because a quantity has a value but the quantum value is the lowest measurable value. However you define that, that is part of the measurement problem in the paradox. So we're dealing with an interesting monopole, that if indeed the proton can be said to be exhibiting the gravitational field, which then becomes an integral field with the presence of many protons, their force fields essentially overlap. This has to be dubbed a theory. This is a hypothetical formulation because the quantum of gravity has not been explicitly discovered. It is being sought, and it's being sought in some very strange modeling approaches, which we will disregard for the time being because it's rather confusing. I deal in geometry whose essential nature is simplicity. It is related directly to mathematics, as I've shown you, and whether or not you were already fully aware of that, I hope that you do accept that statement, that mathematics is a tool of geometry. The universe is non-mathematical except in the sense that it is geometrical. We see spheres at all scales. This was discovered in the 20th century. Although we knew the Earth was a sphere and the Sun, and therefore all stars, are essentially spheres, that's a fair statement. The sphericity of such a macroscale object as a star is rather part of the paradox as well, because it's holding itself together as a body in space due to gravitational force, which is half the time called a pseudo-force. There is a specific reason which is not often explicitly stated. In a science presentation such as I attempt to present, I follow the strict rules of science, which dictates that in order to get to the cutting edge, in order to answer some problem, in this case the quantum of gravity, you have to recapitulate what is already known so that we can proceed from known suppositions. Preferably proved ones. That's actually strict science. Proved statements that we already know, leading, we intend, to a solution to a specific question. The nature of the question of the quantum of gravity, or quantum gravity, has to do with the fact that it's monopolar, whereas electromagnetism is not. It's bipolar, that is dipolar with a D, simply meaning that there's a north and a south end of an electromagnetic phenomenon such as a magnet. So we do have an electrodynamic approach to one aspect of centripetal force, but centripetal force is only one of the forces exhibited by magnetism. Because of the relationship between the plus and the minus poles, you yourself know from certainly experiments you did as a child, with two magnets, the two magnets, if they're oriented plus to minus, will exhibit centripetal force on a common center between their force fields and will actually move toward each other. Einstein essentially named that spooky action at a distance, and it also baffled Newton, who did not attempt to explain that, because Newton's explicit premise in his approach to science was to gain mathematically provable statements. He was not interested in what he considered to be philosophy, although science does have a department for that necessarily, because everything we learn in science, if it's not destined for technology, which is a legitimate branch of science, but science overall has as its goal explaining the universe to the human mind, which is quite a philosophical framework or orientation, because we're not sure what questions to ask, because we're not sure what the solution might be. Currently, we're talking at very high level, as has been the case really for centuries and millennia, of what does the universe actually say to us. That seems like a very simple, even cliche statement, but I consider it to be profound, because we're soliciting the universe for solutions. The question then would be, solutions to what? We're not sure. Each one of us as a human just arrived here with an essentially infinite amount of time preceding us where we were not here. And now for about 70 years, certainly in my case 70 years, you try to figure out the answers to questions that you may have about the universe. I call that science. Science itself has called itself that for a long time. But science is many, many things. Now, to get back on track, I always like to give a little bracketing information for where we're at. This is a fundamental question, which you would expect, just intuitively, will probably be rather difficult to solve if you're looking for an absolute basis of some phenomenon in the universe. We even address the universe itself. I consider that to be a bit precipitous, but it's hardly avoidable. Maybe we could say something about the universe itself as a unit. Well, we're trying, and we use theory until we can get the solution. Now, in the case of gravity, we do know that it's logical. Newton essentially proved that, and Kepler, his forebear, did a very good job in mathematizing the relationships involved in celestial mechanics, which of course is based on gravity. So we do see, just looking out into the sky, what gravity implies. The Earth goes around the sun because the Earth is a smaller gravitational body. It does form a barycenter, which is between the two foci of gravity. But since the Earth is much smaller, I believe on the scale of 1,000,000 times smaller in mass, it exhibits a circular, really an elliptical orbit around the sun, as do all the planets. That is gravity. We ourselves experience gravity on Earth. I instruct my students, although my real students won't actually enact this experiment, they'll do it as a Gedanken experiment, but I tell my students at a young age, pre-high school, stand up from your chair. And when you do, you're making a straight line through what's called your pranic axis, according to an Eastern formulation or model. Your pranic axis, which goes directly through the center of your body, in some sense, from the soles of your feet to the top of your head, is a straight line from the center of gravity to the edge of the universe. That's called a ray. And because the Earth is a sphere, you can draw a diametrically opposite line from the center through the other side of the Earth. And we like to think of that as Australia, although you'd actually have to plot where that line actually comes out in the southern hemisphere, in the eastern hemisphere that way. There could be someone in Australia standing up from their chair, and your lines are essentially the same line but in opposite directions, called polar opposite direction. That does not fully describe gravity on the sphere, which I related to you can be geometrically formulated as a different kind of line, technically a line in another dimension. It's an integral dimension called the spheric dimension, in this case going out. Actually, in this case, going in. The gravitational center is the center of the protonic mass called the Earth. So there is a center to gravity. The problem with that is whether it's a force or a pseudo-force, which I'll discuss briefly as I have before. Whether it's considered to be a force or a pseudo-force, it's one of the two. It's monopolar, which violates a fundamental law of the universe called the conservation of force. This is an extension of the conservation of energy, which is a conserved force. Force is construed as an expression of energy. In Newtonian force, it can be linear. For instance, the path of a jet through the sky could be considered to be a Newtonian line. A straight line, that's Newtonian force. Due to the thrust coming out of the jet, it attains forward momentum, and that exhibits the force that drives it forward in a Newtonian trajectory. In the case of gravity, it is not a Newtonian trajectory, it is an integral trajectory of those lines. Because all the lines from the surface, you can just put it this way, exhibit a straight line toward the center. So the integral of all those straight lines toward the center constitutes one line in spherical space. This is a reasonable formulation, but you may never have heard it because essentially I discovered it. So, I'm stating the obvious. That does not constitute a discovery, but it leads to a discovery. The monopolar aspect of gravity is one of the most baffling questions ever put to the human mind. The way it is expressed in cutting-edge science now, today, in our contemporary world of 2025 AD, we are considering the quantum of gravity because we believe we might find it. I don't argue with that. I believe we can say that we've already discovered the quantum of gravity, which would, in order for that to be a correct statement, would have to satisfy all the definitions of what is a quantum and all the definitions of what is gravity. Can we say that there is a quantum of gravity? We could, but we don't. I've only seen it alluded to a couple of times, but I've never seen it directly stated. My hypothesis that you could reasonably, in a modeling form looking for the actual solution, you hypothetically state that the proton is the quantum of gravity. If you do that, you then have to prove that the proton is a quantum. That has been proved for the simple reason that all protons are the same and there's nothing inside. However, due to the work done at the subatomic level, particularly in the cyclotrons, which are now called hadron colliders, we have discovered that there is something of some nature inside the proton. However, we've never penetrated the proton. Mathematically, it has been shown, I believe conclusively so, by a man named Gelman, that there is a triad or trinary, a three-component mathematical system. Gelman was able to show that this is a reasonable formulation of the dynamics of the proton, which now has a name, although it's not greatly important. It's called chromodynamics. And that is the cutting edge of physics in terms of the interior of the proton. What you and I shall be concerned with today will not go into that extreme depth, although I have addressed it and I have a lot to say about that, because I believe I've made some discoveries based on Gelman's mathematical insight. Alright, so much for that. When we are looking at the... Let me make sure I get this here. There we are. When we are looking at the proton, we are looking at a particle that is a quantum particle by the strict definition, because all protons are the same. Electrons are not. That little blue dot shown basically on the circumference of a force field is an electron in a simplex hydrogen atom. That is what this diagram intends to show, is the relationship in spherical space between a proton, which is always at the center of a system, and an electron, which is never at the center of any system, unless you refer to the electron itself as a system, which we do, but we cannot identify a center to the electron. Instead, it is said to have a locality, and the equation of the electron and essentially going to the equation of the photon is nothing at all like the equation for the proton. For the simple geometric reason, keeping this simple, which it should be, the proton makes its own center, which you can see in this diagram. The blue shaded circumference indicates through visual clues that the line, that is the curved line, which is a circle, represents the spherical surface of the protonic force field. None of that is theoretical. That is already known and has been known for about a century, that the proton is always at the center. And you could leave it at that, but if you wanted to give it an object in the grammatical sense, it is the center of a space field. It is a space field that is around the proton. So the proton may be said to be that red dot, whose radius is fairly well determined now, certainly within, I'll just say nothing can be exactly stated at this scale, due to the Heisenberg uncertainty principle, which also applies to the proton, because it does have what could be called an impenetrable core. That is why it is called a particle. In the Hadron colliders, as you're certainly aware, when two protons are forced to collide because one of the protons has relativistic velocity, actually an enormous amount of velocity compared with the other proton, that is a form of energy expressed as relative velocity. And so that is potential energy about to be released if the two protonic cores can be forced to collide. You can see that there is actually another barrier besides the surface of the red protonic core, which is essentially the particle itself, because the particle is inseparable from that circle surrounding it that's highlighted in blue. That is the radius, which you must think of not as a single line, but as the integral line going out from the center, is indicative of the limit of a force field, beyond which the force field no longer is operative. That needs to be explained. It has been explained. And it is the most remarkable thing, I think, to say in context here, that the difference between the force field surface, inside of which the electron will not go and has we've not been able to force an electron to violate that force field. So the blue dot shows on one radial line, that is a derivative line of the total line going out in all directions from the center, that electron is occupying the force field limit. So that's a Lagrangian surface. That's my term. I invented it in order to describe my discovery. But I wish to point out, because no discoverer is ever alone, that this essential boundary between the force field of the proton and what is outside, just going further out from the surface of the force field, that boundary, that spherical boundary, is the boundary of two force fields. The question then, what is the relationship between those two force fields? The one on the inside, which forms a surface going from the center out, beyond which it is no longer operative, that boundary has another side, the outer side. And what is that? The electron shows us what that is. Because the electron, if it's not on that circumference, but it's outside the circumference, is invariably drawn toward that proton. Assuming no other forces are active, a stationary, that is, a non-relativistically moving electron that's placed in the white area somewhere outside the force field will go toward the center of the force field on a linear trajectory, but as a spherical surface. We do know that the electron is essentially spherical, although that's really getting down to some interesting distinctions. But the electron must be spherical. We do know that. It's just difficult to say exactly any more than that. That's the quantum paradox of the electron. It does make a locality in space which is spherical, but it becomes probabilistic after that. You're not sure exactly you're not exactly sure what it is because it doesn't have a specific position. Now when the electron goes toward the proton, like this, or from up here it would be coming in from that angle, going straight toward the center, towards that bullseye shown as a plus inside the red dot, the electron is trying to reach that. The fact that it can't is a most interesting phenomenon, which basically describes a hydrogen atom. So you're looking at a diagram of the hydrogen atom relationship between one proton and one electron, where you can see by what is called a tangent line that when an electron comes toward the proton and then goes into that circular line, it goes at a right angle. But it only goes at a right angle at the actual point of tangency, which is a contradiction, because a point, by definition, does not exist. So what actually happens when the electron changes trajectory? Essentially, if it's coming toward me, I'll go this way. If the electron is coming toward me, and say my head is the proton, it comes directly toward the center of the proton, but then when it reaches that radius, it goes at a right angle all the way around the proton. What we would like to know is how that electron transitions through what might be construed as a hard right angle. That would be the mathematical solution according to the Newtonian calculus. But you could see that that is physically impossible, because it would be as if it came towards this square and then stopped and went straight up. So that's not what happens. What does happen was discovered over 250 years ago by a natural philosopher, which was the term used essentially for a scientist. Science has different aspects, and when you say that you're talking about scientific philosophy, you're not trying to guess. It's not philosophy in terms of a more loosely construed form of logic. We use strict binary logic. We make propositions which we can prove to be true. That's the goal. In this case, what has not been discovered is the actual transition geometry between these two spherical surfaces. The electron comes in as a sphere and essentially contacts the force field of the proton, but you can see there's already a force involved. The electron is being drawn toward the proton by what is termed electrostatic charge relationship, which initiates a force relationship. Because the electron, by its very nature, its properties, is inevitably drawn toward that proton, actually from any distance, going to infinity on an asymptotic relationship, which means no matter how far away that electron is from the proton, it will start to move toward it. At close range, it's accelerating because the attractive force of the protonic force field is attracting the electron and accelerating it. It doesn't attract it on a linear a linear velocity. It's accelerating toward the proton. So when it reaches the surface of the till then attractive force field, the force field reverses and repels the electron. This was discovered by Rudger Yosip Boscovic, who had no instrumentation with which to probe what he felt that he had discovered using pure algebra, which is quite a remarkable statement. And he claims, and I checked, I do have 3 copies of his book, which I've tried to read all the way through. It's a bit dense, but at the start is most of what he wants to say explicitly, which he then attempts to prove, and I believe he did prove. He's never been refuted. He's actually never been challenged. What he has been ignored. Nobody understood what he said. Newton and Leibniz had already died, and nobody else, in the remotest degree that I've been able to discover in my researches, nobody understood what Rudger discovered. But it wasn't challenged and it was never refuted. However, certain men, of course, knew about Boscovic because he was the foremost physicist following the era of Leibniz and Newton. So Boscovic is a most interesting character. What we'll be doing today is exploring that in quite a bit more detail, and here is our introduction to that force curve. What you're seeing here, and just accept what I say until I explain it, you may already see just by looking at this that this is actually depicting the force relationship between the electron and the proton. Now, this particular diagram, taken from Wikipedia on the nuclear force, which is actually here the strong force, because there are more than one nuclear force. This is a depiction of the strong force, which is the binding force tying 2 protons together. So we're now talking about a different relationship, not between the electron and the proton, but the proton and the proton. And now, don't let this shock you, but I'm going to show you another diagram that Boscovic drew about 250 years ago, which is a more complex curve, but it's the curve of relationship between an electron and a proton. There it is. That is the very famous now, certainly in Europe, Boscovic force curve. And I want you to see just a bit more of this. So I'm just going to shrink it down so I can extend this side, because you need to see the asymptotic curve. And now you can see the asymptosis that's at the extreme right of this diagram. You need to first understand what is being depicted here in terms of the lines, one of which, well, 2 of which are straight, because this is a Cartesian projection essentially, which has simply a vertical aspect on a plane and a horizontal aspect on the plane. The horizontal aspect on the plane is depicted by this horizontal line, which indicates space, which is a bit of a mind stretch, but you have to first realize, as I'm sure you do, that this is a projection downward to a 2D planar image of a spherical phenomenon. So the horizontal line is space. In the older nomenclature, that's called the abscissa. We today call it the x-axis, and that is simply one of the 2 aspects of the plane shown here, a typical 2D projection, because this is 1D and this is the perpendicular dimension. There is only one spatial aspect here, and it's not anywhere vertically. The space aspect is only on the line. That's the only depiction of space here. Now, this diagram also has a pronounced curved line. That is not a spatial line. It is a force relationship algebraic curve. That curved line is not going through space. That's rather a challenge, I think, for most minds, including my own. I really spent a huge amount of time analyzing this very important diagram, because what you're looking at is now known to be accurate. Accurate what? What is it showing? It's showing the force relationship between an electron and a protonic core, which in this case has more than one proton, because there's more than one up-down curve. Now, just to remind you, we had been looking at this. And you can see that that is a single curve, you could say, or you could say it's two curves. But as it's drawn as a single line, you could say that it's one composite curve, which is two ways of saying the same thing. That will be significant, as you shall see. Now that is the relationship between a proton and a proton at their closest range. This would have something to do with gravity because the proton does exhibit centripetal force, which could be said to be a quantization of gravity, although that would have to be proved. That has not been proved, although I believe I have proved it. So that's where we're going, is to prove that the proton is the quantum of gravity, eliciting two paradoxical problems, which I attempted to outline, but I'm sure you can recall. Gravity is monopolar, which violates the conservation law of the universe, because that would imply that the proton is a black hole. If it indeed is bending space in, there's an action that bends space, and that would be called either a force or a pseudo-force. Is gravity a pseudo-force? Half of all physicists say it is, which means essentially it doesn't show any motion. Gravity is a static exhibition of some pseudo-force in that case. It's not really a force because there's no motion. A force exhibits motion. A force actually can be considered to be identified with a motion, whereas gravity is not. Although you may have an objection that it does affect the motion of another body. For instance, the Earth around the Sun is being influenced by gravity. Well, is that a force? Newton said that it had to be because it implies acceleration. But then Einstein came along and said, oh no, that's not necessarily acceleration, because you can't tell the difference between the Newtonian acceleration and a static curvature of space. So you could say, equivalently, that it's not a force. It's simply the geometry of space. My hypothetical resolution of that is you're saying the same thing in two different ways, but you must not discount the nature of force, which now, according to my, I believe, better formulation of this rather strange dichotomy, is it a force or not? Well, what you're saying is it motion or not? What you're saying is it mathematical or is it geometric? Well, I think you already know that those should amount to the same thing if we're using our mathematics correctly. So that's really the situation that I attempt to address here. The electrons always repel, and they cannot be forced to collide. They won't. They simply don't. The only time electrons may be said to be in some closer proximity than just two separate electrons which repel forever is when they're in a standing wave form around a proton, in which case the inner shell can have one or two electrons, depending on if there are one or two protons. And that describes the inner shell of the atom, which can have either one electron or two electrons, but no more than that, so it is quantized. So the inner electron shell of any atom can only have, at most, two electrons. If there are 0 electrons, the proton is considered to be an ion, and it's basically charged in the respect that if it can capture an electron, it will. And the electrons are always somehow attempting to move toward a proton, no matter where they are, so eventually an ion will capture a free electron, and a free electron will eventually be captured by a proton if there's just single protons roaming around. Now, protons can combine, as we know, in the center. And when they do, they've overcome the strong force. Or you could say they've combined according to the strong force. That's the definition of the strong force, is that it is the force that causes two protons to combine. That is centripetal force, because it's drawing toward a common center. It's not repelling, it's attracting. So these are two primary forces in spherical space. That's actually a major discovery, although you could say it's already known. You just never hear it modeled that way because it's not the preferred model. I say that that is probably worth exploring, and I have done so. So I'm expressing to you my research, which is very largely based on Boscovic's research, which was accomplished before the electron and proton had been discovered. He did not even know there was such a thing as an atom. Certainly Newton didn't, well, neither did Boscovic or indeed Leibniz. They attempted to each formulate their own theory, but none of them thought that it was of permanent validity because they simply didn't know. Well, if you don't know, that's not quite science. Boscovic claimed and was convinced that he had discovered the force relationship at the ultimate inner scale. That would be the quantum scale. So let's talk about this diagram, which looks complicated. Even Boscovic made a note that is kind of overloaded with letters. You could disregard the letters. All he was doing was using the same diagram to illustrate several principles, each of which required its own set of letters. So you could disregard the letters. And in fact, I should have a more simplified view, but I wasn't able to immediately find it in my database. So this is essentially the correct Boscovic force curve. Now over here, you'll see there is a vertical line, which is the y-axis. So what's at the origin, where the y and x-axis cross? That is the center of a particle. We know today that that has to be a proton. Boscovic simply called it a particle, but he was correct in stating what we now know in his own words, that that is the center of a system. The other particle is somewhere on that space line. And remember, space is only on that line. So to complete the description of this diagram, so you'll know what everything is, so that we can get to the explanation of what this diagram purports to show, the vertical axis, way over here, has a reflection to the extreme left, and you only see part of it. But what it is the exact same force curve going in the other direction. And you may ask, what does that mean? It's the other side of the sphere. So all it is the polar reflections, so therefore it can be disregarded. Because this does show a spherical relationship in a projection downward to where we can see it on a flat plane. All right. The vertical aspect, which I will now expand this just a little bit. I don't know how this got off kilter, but you should see... Oh, actually, you don't see it here. There is no metric for this. Boscovic had no way of putting graph marks because he didn't know the scale exactly. We today can put scale marks on there. And this is what I was attempting to realign here, is over, and I think you can see a pointer. My pointer is now moving to the origin. And that is where the space line, the horizontal line, crosses the force relationship line. Above the line is either repulsive force or attractive force. And whichever one it is, in the opposite direction, here going down, would be the opposite force. A critical question, you would certainly have to say, is which is which? And it's a remarkable statement which caused me some confusion for a while, although it did lead to a discovery. This diagram shows the repulsive force on one side of the spaceline, whereas this one shows the opposite force, the inverted force relationship. And that is because this curve of the strong force between two protons is between two like-charged particles, whereas this one is between two unlike-charged particles. I must apologize again. There was an incursion of the gardeners who run some power mowers. So that was only a nanosecond for you, but that was actually about a half-hour delay. And I'm sorry, I am sweating profusely. I have to keep the door shut. But you probably won't see, except from me rubbing my face, that I'm pouring sweat. So the diagram here that we're looking at is indeed an accurate portrayal of the Bohr atom having necessarily more than one proton at the core, because there are multiple curves. Those curves represent a force balance between two forces. In this case, Boscovic has set this up not knowing the distinction between the electron and the proton, and therefore projecting this as the relationship between two general particles of which he had no further information. It is remarkable that he correctly identified the proton without knowing that's what he had done. He simply called these two particles in relationship on that space line, the horizontal line. The curved line can be read statically as a simple map of the force relationship between the two particles at any distance, what we would say any point on the space line. By reading up or reading down, you can see whether there is an attractive force and how much attractive force, and a repulsive force, which is which. He stated which is which here due to his algebraic curve extrapolation here, which is now known to be correct. He actually got the correct relationship between a proton and an electron without knowing that they were different. He simply called them particles that had a force relationship between them at all places, with the exception of certain points on the line where the force line crosses. Where the curved line intersects with the space line, there is no force, because that is, vertically speaking, it's zero force. There is zero force where the curved line crosses, although at all other places there is either an attractive or a repulsive force. So this is a valid depiction of the force balance system of a multiprotonic atom. A tremendous intuitive breakthrough. He could not actually prove this by experimental means. That was accomplished in the 1920s, although it was a process. The discovery of the proton, such that it can be now stated accurately that it is always at the center of the force system. So the proton exudes a force. That is inaccurate. I did not state that correctly. The proton exudes two forces, and they alternate. That could be designated with a qualifier, perhaps a harmonic relationship. It would have to be harmonic in order to conserve the force itself, which would be a perfect balance between repulsive and attractive force, such that they can be algebraically proved to equal zero when they're added together. Essentially, the symmetry that Emmy Noether identified is also always associated with a conserved force. There will be a symmetry. That is indeed the symmetry exhibited by this curve when you examine it both vertically and horizontally. Now, you can see that the humps, that is, the separate curves, of which there appear to be 3 here, would necessarily be balanced. In order to see that balance, you would have to do some computations, but you can visually see that it looks like there is indeed a force balance. Because the humps above the line do not vary greatly vertically with the humps below the line, and that would require some more detailed explanation to draw that out so that it could be proved. But it is showing some force relationship that exhibits, most apparently, a force balance. Now, what we would like to discuss is the nature of the two forces such that it acts on another particle. In this case, we can look at this not statically but dynamically as depicting what happens when an electron approaches the proton. On the extreme right in this direction, you see there is an asymptotic curve below the line. We will have to decide somehow which is which. Which did Boscovic say is the repulsive force? Is it below the line or is it above the line? From what we now know, in the class of science called electrodynamics, the electron does achieve a final inner orbit if there's only one proton and one electron. So we turn now to this diagram, which actually depicts that, but you know that it's going to be inverted because this is a proton-proton relationship. So this asymptotic curve, and I believe you can see my pointer here, the asymptotic curve going up is asymptotic to some vertical line, which is approximately here. Because this vertically rising line never touches the vertical line, that is the definition of an asymptotic curve. It essentially goes to infinity without becoming parallel. So this is a violation of Euclid's parallel postulate. There's still some noise outside, so I'll return for you in under a second. Very well, we're back again. The noise has subsided outside. So this simple diagram does show the relationship between two particles according to the Boscovic force curve. It is the innermost curve of this multiple series of curves. You see that the innermost curve dips down. I want to be sure that you can see the pointer. It dips down and then essentially goes up and keeps going up. Well, that's a very interesting relationship because that is an asymptotic curve going up. And I had said that what that implies is that the force curve never becomes parallel to the vertical line. But that's an incomplete statement. There's one more statement that must be made. It also never intersects that line. Now I draw your attention over here to the right side where there is a final lower curve, and then going in the opposite direction it comes up and becomes asymptotic to the horizontal line on the lower side, whereby that curve also extends to infinity without ever becoming parallel to the spaceline and also never intersects it. Now I wish to draw your attention to where the force line intersects the spaceline. That would be here and here. and here again, and then here one almost last time, and then one last intersection before it shoots asymptotically vertically. What does that imply? We need to compare these. This is the easier one to describe, I would say, because it shows a relationship between the space dimension going to infinity to the right and the force line that never goes away. That is, it never intersects any further. So that is infinite space. And as space extends infinitely to the right, the force goes closer and closer to zero without ever reaching zero force, whichever force it is, attractive or repulsive. Now we need to interpret the two forces for each of the curves. This is the proton-electron relationship, which can be simplified to the hydrogen single proton curve. This would be the innermost curve of the prior curve, but if so, it's no longer depicting the strong force. These force curves are invertible, and so it's critically necessary to decide the binary decision: which is which is repulsive, and which is attractive. It depends on which intrinsic force is being described, which is a strange thing to say, which, if it confuses you, believe me, it has confused everybody. And so it's necessary now to simplify what I said so that you can see it. This curve can be interpreted either as electron-proton or proton-proton. But whichever one you're attempting to depict, the force relationship is inverted from plus plus to plus minus. So which is repulsive and which is attractive? It depends on if it's the strong force or the electrostatic force in the case of proton-proton. In the case of the proton-electron, there can be only one interpretation, because there's no equivalent strong force between the electron and proton. That also may be a bit baffling, so let me drill down so as to clarify and simplify this so you see the relationship directly. Which is which? Now we have to state clearly which two particles are involved. Here we're going to say that it's the electron and the proton so that we can isolate the innermost curve of the Boscovic relationship, which is indeed, as we now know, the proton-electron relationship. So this shows a proton, as always, at the origin, that is the center of its force field, and the two lines attempting to close on that origin, only one is the space line, that is the horizontal line. That obviously does intersect because space does intersect at the origin. However, the force line does not reach the origin. Instead, this force line dips down, coming in from the right, going left, and then it reaches a nadir at 1 femtometer, and then inverts, and does cross the line, the space line, in exactly 1 point. That is the point of equilibrium, what I call the Lagrangian sphere, a legitimate term as I've developed it. You won't find it in the literature. But there is such a thing as a Lagrangian point, as you may be aware, in a two-body system. There are actually 5 of them 2 of which are relatively stable, and 3 of which are relatively unstable. The James Webb Telescope is parked in a Lissajous orbit at one of those virtual points in space in the Earth-Moon two-body system. So that's a Lagrangian point in celestial space. This is not celestial space, it's subatomic space, or you could say atomic space. So the blue line shows the ultimate relationship at closest proximity between one electron and one proton. We can now state which is which in terms of the force relationship above and below the spaceline, because the electron is attracted to the proton at sufficient distance. Coming in from the right on the spaceline is the electron, and the blue line below the spaceline shows attraction. The attractive force increases until it reaches the nadir, where it is maximum attractive force at that range. With relative velocity, in this case we would apply it to the electron, we will say that it has a residual relative velocity whereby it is able to proceed past the nadir, where the acceleration now reaches maximum at the lowest point and then starts to decrease, but it's still attractive force until it crosses the spaceline. If the electron has sufficient forward velocity so that it continues, and now the scale is extremely small. So in this range, where you see this pointer going back and forth, it's going back and forth between the equilibrium point and the limit to which the electron can approach. If it has sufficient forward velocity, it will actually be beyond the equilibrium point, and then you can read up to see the repulsive force, indicating that the electron, as it's proceeding forward on the spaceline, cannot go beyond this point, because that is the intersection of the imaginary vertical line. That line is not shown here, but you can see it in your mind. If the electron continues to move forward, it's encountering increasing repulsive force so that it will stop somewhere along the way. It will never reach this point. Somewhere between here and here, it will slow down and stop, and then the repulsive force will drive it backwards. And when it is driven backwards, it will continue under the impetus of the repulsive force of the proton back until it reaches the equilibrium point, and then it will stabilize until it spatially stops at the exact radius of the protonic centrifugal force field. That is repulsive force with respect to the electron. So now we've identified one of the keys to understanding this entire force curve system for the atom, which is somewhat complex, as you can tell, but we've now gotten the key, and now we can unravel the entire thing to fully understand this incredible force balance system. The electron, at the point where you see the arrow, is in its electronic shell, and that makes hydrogen. So that is the depiction of the radius of the hydrogen atom, where it's stable forever. The fact that it's stable confounded the early researchers in atomic physics, because it leads to the equivalent of the ultraviolet catastrophe, because the electron, as it's orbiting the proton, should be losing energy, but it's not. And the reason it's not is that it's not a particle. It's a standing wave, which is harmonically balanced on the intersection of two spheric force fields, one of which is centrifugal force on the inside, going towards the center of the proton, and the other force is on the outside, and it's the reciprocal force. It's the centripetal force that draws the electron to the edge of the centrifugal force, and thus you can see that right here the force field inverts. That's the inversion of a spherical force field. All right, that's a little over an hour. That's probably enough for one day, or at least for this session. I'll be back later to give you the fuller explanation of the quantum of gravity, which will lead us into some amazing discoveries that I made. I hope you're entranced, or you're at least curious. You trust me to the point that you're willing to hear the proof sequence. If you're not, because you don't trust me, because obviously I'm discovering something which is most unlikely, I wouldn't blame you a bit, and you please go in peace. But I do hope you tune in. It's the most important discovery in the history of science, and it's more than one discovery that I've made. Thank you very much for your patience through this most interesting descent into the heart of all things, which is a two-force system that describes universal space from a universal reference frame, which was the goal of Einstein that he never achieved and nobody ever has. Dirac tried to approach this as well and also failed due to the mathematical system in use, one component linear numbers, which are now fully inadequate to describe reality, as I've shown. As you could probably guess, this cannot be accepted because it's true. We'll be right back. Keep looking up. If I don't see you between now and nightfall, wherever you are, look at the night sky. It's the best time you'll ever spend on Earth. Thank you.